Here's another example of using the Biot-Savart law. Let's say you want to calculate the magnetic field at this point here at the center of a semicircular arc carrying current I, but wires extending out from great distances straight as well. So what is the total field at this point due to all this current carrying wire? Remember, currents create magnetism, so all these currents might possibly contribute to the magnetic field. Using the Biot-Savart law, it's helpful to think about the vector definition here. If you take a little piece of current out here on this straight section and you label it, let's say ds as its length, ds points the same way as the current, I can then define r hat and r. R would be this distance from, let me change this r to a big R, from that piece you picked out to where you want to know the field. And r hat is a vector then that points in that direction, a unit vector that points from ds out towards that point. So notice the angle between ds and r hat is 0 degrees. So theta is 0 degrees, the angle between ds and r hat. From our Biot-Savart law formula, theta is the angle between ds and r hat. So sine of theta, in this case, is going to be 0, because sine of 0 is 0. So that means this whole straight piece has no magnetic field over here at this point, because ds and r hat will always point the same way. You could do the same argument over here. A piece of current pointing this way has an r hat vector pointing that way. Now theta is 180 degrees. Okay, the angle between ds and r hat pointing back at that point. Sine of 180 is also 0. So we can ignore this piece here. There's no magnetic field at this center point due to either of these two straight pieces of current here. Okay, so that means we just got to worry about the semicircular arc. So let's take a piece of current. Here is a little ds vector. And we need to define r and r hat. We're using big R now for the radius. And r hat, I guess I'll call it big R hat, points in that direction. But notice, because ds is infinitesimally small, it's tangent to the circle. R hat is a radial line. So that means the angle between those two is 90 degrees. So theta is 90 degrees now. Sine of 90 is equal to 1. So we're going to get a nice big field at this point due to that little piece of current there. So I can plug in terms in this equation. So the tiny field at this point, dB, equals mu naught I over 4 pi ds sine of 90 over r squared, where I'm using big R for the radius of that circle. Okay, so all I've done is really use big R, and I plug in theta is 90. Of course, sine of 90 is 1, so we can get rid of that. And what do you got? Well, big R is a constant here. Anywhere on this semicircular arc, you're a distance big R to the center. So that means we can say the net magnetic field, which is the sum of all the individual fields, in other words, integrating dB, is simply mu naught I over 4 pi big R squared integral ds. And again, r squared is a constant. It comes out of the integral. Okay, so integral ds is quite easy. It's just the length, or it's the sum of all the ds's that make up this semicircular arc. So integral ds is simply the length of that arc. Okay, so this is the length of the semicircular arc, which is the circumference divided by 2 in this case. Right? Circumference is the distance around a circle. This is half of a circle. So we can write then that the magnetic field is mu naught I over 4 pi big R squared times integral ds, which is 2 pi r over 2. So that's just a pi r I could cancel a pi, I could cancel an r, and you get an equation that looks like this, mu naught I over 4r. That is the magnetic field magnitude at the center of the circle. But what about the direction? Well, you can use a whole variety of right-hand rules to figure out the direction. We can use our first right-hand rule, fingers here in the direction of ds, curl towards r hat, thumb points in. So the magnetic field vector is going to be in here due to that piece of current. So I'll draw an X representing that. You could also just remember field circle wires. You got a current going that way. If you point your thumb in the direction of current and wrap your hand around in a circle, your fingers poke in down below. There's another right-hand rule you can use for circular arcs or circles. You curl your fingers of your right hand along the arc in the direction that the current travels. So that's this way. Your thumb of your right hand will point in the direction of the field in the middle, which is again in. So the net magnetic field is into the board. Okay, so the magnitude is this value, and it points into the board for the direction. And of course, the units would be in teslas. Oh yeah, there's a homework question just like this.